So first of all, I would like to thank the University of Chile for the invitation. It's always a pleasure to be back at Chile. I would like also to thank the president of this event all the way, also both the scientific and organizing committees. So, okay, I have a problem with my voice. So, I would like also, dear honorable colleagues, our beloved PhD students, our guests from foreign countries, so welcome and good morning to everyone. Today I have the pleasure to present some of my expertise in LC development. So in the next, I'm going not to exceed 30 minutes. So I'm going to speak about LC and LC-LC two-dimensional chromatography, the analysis of bioactive compounds. So as we know, a lot of researchers are working on the analysis of bioactive compounds, on the biological activities. We do have a lot of bioactive compounds in biological activities like food. So most of research lately are concentrated on the study of natural compounds, on biological activities. These bioactive compounds like polyphenols, alkaloids, carotenoids, vitamins, saponin, etc. Despite there are a lot of studies focused on this, but still the research of new bioactive compounds is conducted everywhere in the world because we are interested in discovering new compounds with new biological activities. So analytical methods should be selective in order to study these bioactive compounds, and it should be also sensitive enough in order to detect minor compounds, because sometimes even minor compounds have stronger biological activities than major compounds. So for this, there are a lot of techniques used in order to study these bioactive compounds, but still chromatography is the most important technique that is used in order to study these molecules. Before talking about analytical techniques, LC and LC, I want to speak about extraction method and the effect of the extraction method on the analysis in LC, because it's the first step and it's a very important step, because all the rest of the result depends on the extraction method. The analytical part and also the biological part, because most of the time researchers, they choose not a good method for extraction, and it affects the result of the analytical part and also the biological part. So the choice of the the extraction method is very important. So the qualitative and quantitative studies of these bioactive compounds rely on this, the selection of an appropriate extraction method. So in chromatography, there are a lot of developments on mobile phases, on different columns, on detectors, but still the success of this technique depends on the extraction method of this bioactive compound. So there are many factors affecting the extraction. The matrix properties of the sample, when you do the extraction from, for example, from a leaf and from the seed, it's not the same matrix, so it should be different and different extraction techniques. We have also the type of solvent. Professor in the morning, he spoke about green chemistry, and the choice of solvent is very important, and also especially polarity of the solvent and polarity of analyte are important. Temperature of extraction, pressure, and time of extraction are very important factors that affect the analysis. So when we speak about the solvent selection, the first thing is the polarity. When you choose a solvent, you should make sure that its polarity is the same as your analyte polarity. For example, you cannot use, for example, water for the extraction of phenolic or polyphenols, because polyphenols, and especially flavonoids, they are not polar, and water is really polar. So we have to respect that. Also, for example, anthocyanin are a very polar compound, so it's better to use water for the extraction of anthocyanin. For the solvent purity, when we extract bioactive compound to analyze in LC, it's preferable to use LC grade solvent because the other solvents are low purity, and when we analyze them in with LC, we do have a problem of signals. The baseline is bad, and also we have ghost peaks which belong to the solvent, not the sample, and you will have false results. So also, the choice of high purity solvent like LC grade solvent minimize interference. So when we say interference in LC, it means any signal or any peak that doesn't belong to the sample. Because most of the time when you have a chromatogram, some of the peak belongs to your sample and others they are ghost peak that belong to the solvent because the solvent is not a high purity LC grade. The second is the choice of extraction method. So there are a lot of extraction methods, classic one, modern one, but and this method affects the result of LC. For example, if you work with Soxy method, so it gives a high yield for thermostable compounds, but the problem is you extract a lot of impurities and you will have a bad baseline and ghost peaks. For the method that it's used most with our PhD student maceration, so it's simple, low cost, but it's not a good method. So it's low efficiency and it's incomplete extraction. It means that a lot of molecules stay in your sample. You didn't take everything. So for other modern method, like for example, ultrasound assisted extraction and microwave assisted extraction, so they are rapid, high yield, reduced solvent use. So for example, UID, you have higher analyte recovery. There is a comparison between the yield of maceration and with ultrasound, so you have 26% more polyphenol extracted from the same sample with this technique. So this is a selective extraction that minimizes coelution. It means that coelution of impurities. It means that when you use this method, you will have less problem of impurities of ghost peak than the classic method. But the problem of this method is when you use excessive power, so you will degrade your molecule. For example, we have some students working on the extraction with transformation, and in their protocol they use, for example, 45 minutes or 1 hour. You are going to break all the bonds of your molecules and you are degrading your molecules. So what you have at the end of a result is false results, not what exists in your sample. So the second method, the microwave assisted extraction, is the fact of using this heating, rapid heating, so you are going to achieve equilibrium of extraction in just minutes. For example, 12 minutes for CDP. But if you use Soxy, you need 12 hours to achieve this yield. But the risk is the effect of using temperature overheating, so you might fragment and degrade your molecules also. So we have also supercritical CO2. So it's solvent-free, selective, green method. It's a good method. You will have a pure extract with minimal interference, but the problem is polarity. You cannot use it when you want to extract very polar compound like on this end. So these are just examples of extraction method and their effect on the analysis, LC analysis. So what to take into consideration when you use an extraction method is we have solvent to solid ratio. So when you use high solvent ratio, solid ratio, you will have a good yield of extraction, but the cost of the extraction is too high because you are using too much solvent, especially if it's LC grade solvent, which is very expensive. So you will have a problem of the extraction time yesterday. So we have seen some communication on PhD students using 24 hours and 72 hours of extraction. So you don't need this much time in order to extract your molecule. When you extend this much, you will have the degradation of molecule because we have a chemical degradation, we have also enzymatic degradation, and we have the oxidation of molecules. So you have to accept, because it depends on the method you use, but generally 30 minutes is enough in order to extract your molecule if it's selective enough. So the best practice for method development, you should screen solvent with polarities and this to match analyze. It means the same polarity with the sample you are analyzing. You have to optimize the time and temperature to balance heat and stability. You have to use high quality and purity solvents, and of course prioritize green solvent. For example, we have a list of green solvent like ethanol, like propanol-2, like acetone, or we use also for liquefied compounds, oils like olive oil or sunflower oils. So now I'm going to start to speak about LC. This is the first dimension LC, which is a classical LC. It's one chromatography, liquid chromatography. So we have a lot of development in this field. So also we have a development in the choice of the mobile phase. A lot of columns were developed for each type of molecules with different polarities. We have many detectors for each type of molecules. For example, for DAD, that detector for example polyphenol, alkaloids, carotenoids, and we have LED detector, for example, for sugars, or FLD for pesticides. So we have different detectors. This is why it's important when you want to do the extraction to know what do you want to extract. So use the good solvent, the method, then use the appropriate equipment to analyze, because you cannot analyze, for example, tocopherols with that. So this is very important. So even if we have a lot of development in this field, but still we have a problem of collusion. We cannot separate all the compounds, because in plant, for example, we have thousands of molecules, and it's not possible to separate thousands of molecules in just one dimension. So especially if we have compounds that they have a similar structure, for example, isomer or enantiomer, it's we can say impossible to separate them with just one dimension LC. So this is why it's important to use comprehension multidimensional LC, for example, two-dimensional LC. For multidimensional LC, so it's a combination of several chromatography. It means we have multidimensional chromatography in LC and in GC also. If we say two-dimensional, for example, two chromatography, so it can be two LC or GC, for example. So we have a better separation than normal one-dimensional chromatography. We can use different separation modes, different mobile phase. We can use the same mobile phase of all different mobile phases and different system of column, which can give us a better separation chances with our molecules. So in two-dimensional liquid chromatography, so if you can see the image there, so this is the first one is the analysis with just one liquid chromatography. So then you can see in the cut 2, we have collusion. Sometimes the collusion is visible and sometimes it's not. But in the shape of the peak, when it's obvious, you can see that there are two. But when we analyze it in second dimension, you can see that we have 3 compounds, not just 2. So this is why 1D is insufficient in order to analyze isomers. So comprehension to the liquid chromatography is a better choice for the analysis of this type of molecules. So for example here, it's one dimension and second dimension liquid chromatography, we had comparison. So this is the result. The first result is using one chromatography, so you have a lot of peaks, and some peaks the collusion is clear. Just collusion, it means 2 compounds or more are in the same peak. it's not well separated. This is collusion. So sometimes the collusion is obvious, other times it's not. Like for example, when we do second dimension separation, so you can see that the first peak we have two compounds. The second, we can see that we have a collusion, but after separation, we have 4 compounds and otherwise. So the second dimension, we continue the separation of the compounds that we couldn't separate with the first dimension. We do have 2 types of multidimensional chromatography. We have hard-cutting chromatography, 2-dimensional chromatography, and comprehension. The hard-cutting one, it means just a fraction of the sample analyzed in the first dimension will be analyzed in the second. For example, I'm going to screen. I want to analyze just the second peak, which is coeluted. So I'm going to stop the analysis there and switch it to second dimension. I'm not going to take the rest of the sample. This is the hard cutting second dimension. But most of the time, it's the comprehension chromatography which is used. It means the whole sample will be analyzed in the first and in the second chromatography. We have what we call chiral chromatography. It's the separation of isomers. So as we can see, so in the first dimension is achiral. It means we cannot separate the isomers. They do have similar structure, so they the same affinity to mobile and saturating phase. So it's difficult to separate them. But when we use second dimension, which is chiral, so we can separate these compounds. For example, the chromatogram in 1D, so it's a nice chromatogram with a lot of peaks, but it's not a full separation. So we do have a lot of collusion. Some collusion are obvious, other no. So with the second dimension, this is a picture, it's not very clear there, but it's a picture of the second dimension. So the dot, each dot represents a molecule. So we can, for example, in one dimension we have like 20 peaks. In the second dimension we have more than 300 or 400 peaks. So it's sure of better separation. In two-dimensional, like for example, this is the image of second LC. So as you can see, we have the first separation. We have D1 pump with a mobile phase, and we have D2 pump with mobile phases. The mobile phase can be the same or different. So we have the auto-sampler, so we have our sampler. In the auto-sampler then, the molecules sample will be carried out to the column through the mobile phase, then analyzed. So we have the separation in the first column. We have the loop 1 and loop 2. So it's the connection between the first and the second dimension. So we have the second mobile phase that will enter the first loop. The separate molecules from the first separation will enter the loop, and they will carry the eluted compound to the second column. We have a second separation, and the PDA is detector for to see the final result. So of course we can have a second detector as the MS, quadrupole MS in this case. So this is a real photo of LC analysis chromatogram. So we have the first and the second pump. We have our autosampler with our sample, and we have both all the columns are there in the column oven. So the PDA is the detector, the first detector. The CPM is the place where there is the connection between the first and the second dimension. So we have the loop there. And we have a second detector, which is MS here, is the triple quadrupole MS. As you know, in LC we have most of people think that we have just normal and reverse phase LC, but we do have also helium LC. So in the normal phase LC we have saturating phase, which is a column is polar, and the mobile phase is less polar. The reverse phase is the opposite, so the saturating phase is not polar, and the mobile phase is more polar. In the helix phase, the helix is used more for the analysis of polar, very polar compounds. So it's the combination between the first and the second. So we have the stationary phase, so polar, and the mobile phase, which is organic, so less polar. In the LC-LC, because I said that in LC-LC we have two, for example, this is 2D, because we can have 3D. So in 2D we can have two chromatography. So in two chromatography we can have multiple combination. Either we use normal phase with the reverse phase LC. So this is a difficult combination. Why? Because the mobile phases are different, so it's difficult we don't have a good visibility between the first and the second when they are in the loop. When we use LP, reverse phase LC, so it needs a little bit of tuning. Tuning, it means we are going to work on the metal a little bit because it's the same system, but we will not have a problem of visibility because it's the same type of mobile phase. We have also helix system with reverse phase LC. The problem in here is we have a problem of symmetry of the peaks, so some adjustment, but it's a good combination also. So when we say orthogonal separation, it means two separation using two different systems. 5 minutes, okay. So we have here, we can use different type of LC, 2D LC. For example, most of the use is reverse phase LC, 36%. And then we have the helix and reverse phase LC, 34% of all the 2D analysis combinations. So for example, I'm going to speak I'm going to straight to result in order to not exceed the time. So here is the analysis of reverse phase LC to separate the polyphenols in licorice. So you can see in the first separation, we have a mass chromatogram and mass separation for the first dimension. So we were, for example, you can see that we have like 20 peaks in the first dimension, but when they analyze the second dimension, they were able to identify 311 compounds within just 14 minutes. So this is a big difference between the first and second dimension. So here is a result also. As you can see, we have a chromatogram, which is a very bad chromatogram. We don't have any separation there in the first dimension. But after the separation with the second dimension, so we have a better separation, and they were able to identify, to separate 158 compounds in the second dimension. So this is a helix with the reverse phase system. It's more complicated than reverse phase system because we do have a problem of different type of mobile phase, different polarities. So it needs a lot of adjustment. But as they are different systems, it gives us a better chances to have a better separation. So this is, for example, a helix and reverse phase PDA. So here we can see that we have 83 compounds when we use this combination. So this is just a table to summarize. So the comparison between one dimension and second dimension, LC for the separation power, the first dimension is lower and higher in the second dimension. The resolution, it means the separation between colluted compound is limited to the first dimension and enhanced in second dimension. The compound identification is difficult because we do have a lot of collusion because we have to separate the compound in order to identify them. For the second, it's more easier. For the peak purity, we'll have a problem in second, but it's improved in second. So, but the first, of course, the first dimension is easier and faster. The second dimension, we need a lot of work on the method because the pressure, you cannot control the pressure, the tuning, etc. So, an instrument, we need just one instrument to do one dimension. In the second dimension, we need more instruments. So, and it's easy to read the result from the first dimension, of course, because we don't have a lot of compounds. But in second dimension, you have a complex identification. More than 100 compounds to identify. It's going to take a lot of time and work. And for application, generally one dimension, it's simple sample, but second dimension when you have a very rich sample. So to conclude, the extraction method is very important. LC, using multidimensional LC, get a better result. But of course, I know in Algeria it doesn't exist multidimensional LC, so it's very difficult to work with it. So even when it's first dimensional LC, it's not easy. And thank you for your attention.